So today I thought I would continue our discussion of the ways in which double theories, coupled with double models of those theories, can encode common structures of key interest to our group. And you may recall that we've been talking about this in the context of, predominantly in the context of double models for causal loop diagrams thus far. And I'm just going to share my screen here. Taking a long time as it is wont these days. So you may recall that with at the very highest level, when we have a double theory, this serves the role analogous to a schema for our C sets. But instead of having a C set, where the model is a functor from the schema category into the category set, with each object becoming a set and each morphism in the schema category becoming a function between those sets. Instead, what we're dealing with here in this double category theoretic context is we have something analogous not to C sets, but to C categories. In the sense that instead of, well, we have something that is analogous to a schema, instead of each object mapping to a set, each object maps to a category. And functions within, so vertical morphisms within the double theory, analogous to schema, map to functors between these categories. So if we have a morphism, if we have an object A, it maps to a category. Object B maps to a category. And if we have a morphism going from A to B, going between those two objects, a vertical morphism, strict morphism, that turns into a functor between the category for A and the category for B. And the thing that, just like a given functor from a schema category C to set specifies the particular sets to which each object is mapped, to which an object is mapped to the particular set to which it's mapped, and the particular function to which a morphism is mapped in C sets. So our lax double functor specifies the category to which a given object is mapped. And what we saw last time was that pro arrows here, in the context of these double theories, these horizontal morphisms, loose morphisms, turn into profunctors between categories associated with the respective objects. And so if we have a profunctor, a pro arrow from one object to itself, say from V to itself over here, this profunctor here, from V to itself in this double theory, it turns into a profunctor from that category to itself. And we saw last time that together with the built-in morphisms characterized by the Hom profunctor, the sort of the identity profunctor, the profunctor plays the role corresponds to the pro arrow here. The identity pro arrow turns into the Hom profunctor, which defines our morphisms in this category associated with the object. That the Hom profunctor is just what we normally write as Hom of C, right? If we take the Hom from smoking, common nicotine addiction, it gives us the set of arrows from smoking to nicotine addiction. That's the Hom profunctor. And we'll see in another coming session how this plays a really important role in the context of representable functors. But the non-identity pro arrows over in this double category, this one Z sub 2, turn into what are called heteromorphisms or bridges. In this case, going from C, well, the category associated with V, back to that category associated with V. And those encode information that's composable with these other morphisms, because we can have pre-composition and post-composition. And these heteromorphisms can themselves be composed because they go from C to C. So we can compose one from smoking to health to one with one. And then if we have another one, health to commitment to cessation, they could be composed to get one from smoking to commitment to cessation. And we noted for the causal loop diagram, these morphisms encoded by the Hom profunctor, pro arrow, identity pro arrow here, are associated with plus links between variables. And the heteromorphisms are associated with negative links. And V itself here V itself is mapped by the lax double functor into a set of objects within that category. So it is true that you can say at a certain level this lax double functor maps this object to a category, but it's also true that this lax double functor, if you think about it at a much more detail-oriented level, or in the sort of very low level, it maps V to a set. It maps each pro arrow to a each pro arrow to a span, and at the top of that span to one of these ones, and at the top of that span is a set. You may recall one of these sets. At the vertex of that span, the apex of that span. But these spans aren't just any span, they're composable spans. And those rules for composition is encoded by the compositor for this Lax-Double functor gives the rules of composition. But each pro-arrow here has a set associated with it that is the set of arrows associated with it. So for a causal loop diagram here, the set at the top of that span mapped to by this pro-arrow is the set of positive links, in this case, which is empty. And this pro-arrow maps to a set of negative links, of which there are 3 here. So when we have a set of positive ones, these ones would be encoded by the set mapped to at the top of that span mapped to by this, and these negatives are mapped at the top of the span mapped to by this, but they can compose, and there's a set of other properties once you consider the uniter and other features that mean that this is an honest to goodness category. And these profunctors lead to encoding essentially different types of morphisms that by the rules of profunctors, in fact, they can be pre-composed with morphisms and post-composed with morphisms. So you may remember that with profunctors. That means that this is the features of a category and where we can have different types of links is encoded by these self-profunctors. So all of that is a nice story. It's a beautiful story. And it's a story it takes time to understand. You can view it at the micro level in terms of compositors and uniters and these spans mapped to by each of these. Or you can view it at the level of profunctors between these categories, with each category be having been mapped to by a particular object. You can understand it at those different levels. One is more at the assembly language level, the most detailed level, but it's fruitful to be able to zoom up and understand it at a more abstract level in terms of, V turns into a category. And these encode the morphisms in the category, and these encode these other types of morphisms with a different label, in this case, these plus morphisms. And the rules for composition of profunctors, which are specified in the theory, the fact that like Z sub 2 composed with itself gives this profunctor U sub V, the identity profunctor, together with the fact that if you hit Z sub 2 and then you go with the identity profunctor, you get Z sub 2 back, means that you get the rule of signs and composition. You get a minus and minus composed with each other. So one of these heteromorphisms composed end to end with this one composes to be the identity. So that would be this one, and this one composes to be the identity from smoking to commitment to cessation, and so on. So there's a beautiful story here, and it takes time to sink in, but it's very useful to be able to shift between these perspectives. And there are times you want to be able to draw on one, like the V is mapped to a set of objects at a micro level by this profunctor, and yet at another time be able to say, well, essentially V gets mapped to, V together with it's really V together with the Lax-Double functor specify a category. The rules of the Lax-Double functor and the particulars of the Lax-Double functor are such that V turns into a category. This will be very useful for us as we build on Cat Colab. But I want to talk about stock and flow diagrams. or rather system structure diagrams, because stock and flow diagrams in their full generality with formulas aren't really supported yet. Part of one of the challenges for us in the next year is to work with topos to make sure they get properly captured. But I want to talk about the theory associated with them. And this is going to stretch us a little bit more, but it's going to build on this understanding from causal loop diagrams. So I show here from Cat Colab the code implementing the theory that underlies stock and flow diagrams, or rather system structure diagrams within Cat Colab. It's called theory category links. It has a single object, and it has a pro arrow and this pro arrow is associated with something called a tabulator. This is a type of structure, type of categorical, double categorical gadget that we don't need from primitive causal loop diagrams, or excuse me, for the theory of causal loop diagrams. And I'm not going to do it justice here, but I want to give some sense of it roughly, because I'm still working towards grokking exactly the role it plays. But the idea here is that some of you may remember the exponential object. The exponential object, if a category has exponential objects, or so-called internal HOMs, it means that for every HOM SAT in that category, we have an object that represents it. So it's like we have something reified as an object that can represent every HOM set within our category. And this may sound bizarre, but there are a lot of categories, beautiful categories, where this is true. And in fact, every topos has this. The map between the homomorphisms between two graphs, A and B, graph A, graph B, can be described itself as a graph. The set, if we consider set 1, 2, ABC, and set 1, 2, and we imagine all functions between them, all possible binary encodings of 1, 2, 3, all 8 of them, 2 to the third. That's a set. It is itself a set. Set, and indeed FinSet, has internal HOMs, has an exponential object. For any two sets, the set of maps between them is itself a set. It's an object in set. And Hask, the pseudocategory we use to describe types and functions in Haskell, has internal HOMs. After all, maps from ints to bools have a type. You may recall here that the objects are types, right? We have an object for int. We have an object for bool. We have an object for maps from ints to bools. So we have an object that describes the Hom set from ints to bools. And a tabulator could remind you some of that. But there's some differences. And one of them is that it actually describes not a Hom set or of pro arrows from one object to another. So it's not a Hom set of morphisms. It actually describes pro arrows, but it doesn't describe a whole set of pro arrows, like the whole Hom set. It's not that you have an object for the whole Hom set. You have an object for a specific pro arrow. It would be as if in Hask you had a type for a specific function from ABC to, or from ints to bools. Is prime. It would be as if there's an is prime type, or an is even type, is odd type. So, so with tabulators, we have an object that names our particular pro arrow, not the whole Hom set. And it's names a pro arrow, not a vertical morphism, so horizontal morphism. So tabulators turn these sort of pro arrow maps into objects. They give a type to represent pro arrow. Okay, that's pretty nifty, and that's basically what it's taking advantage of here. But it's doing it for a reason. So they have this tabulator, and I can't pretend to understand all of the exact reason for this. I haven't gone and parsed it out in the software, how this is software engineered. But the idea here is that we're turning the pro arrow from X, the object X, to itself, sort of something analogous to this pro arrow, the identity pro arrow, which represents the Hom profunctor. We're taking that pro arrow and we're turning it into an object. But here it's better to think of it. Yes, exploring. Yeah, it's going to turn it into an object, and that's going to be turned into a category that represents the category of elements associated with this Hom profunctor. And basically, that's going to turn into what's called the arrow category of category C. So if we have category C, so this object is going to turn into a category, and that other object will represent the arrow category of this category C. Now, I want to talk with you about the arrow category. So in this arrow category, we're going to be representing the morphisms of C, and this is actually vertical morphisms. Okay, in this arrow category, the objects of this tabulator-induced category, to which this profunctor is mapping, will represent particular morphisms, which are going to be vertical, strict morphisms, representing the flows. So category C here, the category mapped to by this object is going to have as object stocks and as morphisms flows. Remember, you may remember back to this when we had for causal loop diagrams, this object, we said it kind of turned into a category or together with the Lex double functor. It's sort of in this identity pro arrow in the mapping of that, it turns into a category. And here, this turns into a category C. It's a plain old category. It's not a double category. It turns into a category. And the object of this category are stocks, and the morphisms are flows. Remember, we had the same thing here. This object V turned into a category, right? Where certain objects and certain morphisms. And so it is here. We have the category for the stock flow diagram. Now, with causal loop diagrams, we didn't just leave it there, right? We had this category, but we needed something more than that. There, we needed this way of labeling like minus arrows. And those were, we use this kind of profunctor. And so it is here. We have flows here, but we don't have something critical that we need, which is the ability to specify lengths. So we have ability to have stocks, and we have flows between those stocks. Great. But we don't have a way of saying like a flow depends on a stock. How does it depend on a stock? Well, we want to be able to say there's a link from the stock to the flow. And to do that, we need a profunctor. So there's this profunctor between them, and it goes from the category C into the arrow category of C. Okay, so what's this arrow category? Well, you can look it up on NLab or what have you, in CatLab, but basically the arrow category of a category is a construction where the objects of the arrow category for a given category C, the objects of the flows of C, the morphisms in C, the objects of the morphisms in C, which happen to be flows here. So here's category C. It has object stocks, morphisms, flows. And for this arrow category, the arrow category of C, its objects are the morphisms of C, which are flows. So it has objects that are flows. And morphisms in this arrow category, the morphisms, are commutative squares of this form. I've sort of elaborated a diagram from Evan. So we have, this is a commutative square joining one object to another. This is a morphism from this object, which is a flow, to this object, which is a flow. And these are flows. So that's what a morphism from this object to this object exists for every commuting square we have of this form. Where X, Y, Z, W, those are all stocks from category C. This is a flow from stock X to stock Y that, existed here. And this another one exists in this category. And the question is, what are the maps between them? Are there any? Well, there's one for every one of these commuting squares. So how are we going to represent links with this? Okay, this is kind of a curious construction, indeed. Curious indeed. How are we going to represent a link? Well, we're going to use a profunctor, because profunctors are bridges. Remember that? This idea of profunctors as bridges. We explored that in other contexts too, right? We have explored profunctors as bridges between two categories or from one category to itself. And here they're going to be a bridge. It's going to be a bridge from this category to this one. And that bridge is going to be useful for specifying the links. But it's going to lead us to some curious implications, which we are still mulling. Okay. So I'm saying we have a profunctor from C to the arrow category of C. And you may remember that a profunctor is nothing more nor nothing less than a map, a functor from the product category. The first is contravariant times this category here on the right-hand side, arrow of C, to set, right? That's what this profunctor is. It's a functor, a plain old functor from C op cross arrow of C into set. So let's think that through a little bit, right? So, sorry. So let's see how it operates on objects. Well, a functor maps objects to objects. Well, what's an object in this category? Well, it's a pair of an object from C op and an object from arrow of C, arrow category of C. Okay, so it's a pair of objects from each. So what's an object in C op? An object in C op is the same thing as an object in what category? This is the category C op. But an object in C op is the same as an object in, can anyone fill in the blank? In what?
In C.
In C, exactly. What's an object in C? It's a what? Can you see my arrow? What's an object in C?
A stock.
A stock. Good. Okay. And then, so it's an object from this product category is a pair of an object from C, which is a stock, and an object from arrow of C. What's an object from arrow of C? It's a what? What's an object in arrow of C? Here's one right here. What's an object in arrow of C? It's a put me out of my misery. What is it?
A flow.
Okay. Okay, thank you, Eric. It's a flow. So if we have a stock and a flow, we map to a set for that. And that's going to represent the set of links from the stock to that flow, from that stock to that flow. So for each flow in C, we're going to have some set of links from each stock to it. It's going to be the set of links. Remember, links in this simplified primitive stock flow diagram, links go from, yes, I know Yuja can't utter, so she can't say anything, so she's trying to say things in the chat. Sorry, Yuja, I just saw that. So in this primitive representation, links go from stocks to flows. A flow depends in general on the state of the system. For a given stock, there's some set of links from it to any other flow. For many of those stock flow pairs, it may be empty if there's no dependence of that flow on that stock, but it allows us to have zero or more. Okay, so that kind of makes sense. Links go from stocks to flows. That's kind of what this says. So for every pair of a stock and a flow in C, we have a set. Okay, that's kind of good. But functors like this do more than map objects to objects. What else do they map? What to what? A functor maps objects to objects, and we've just considered that the objects of this get mapped to objects of this, which are sets. So each object of a pair of a stock and a flow gets mapped to a particular set. What else does a functor map? It maps what to what? It maps
Morphisms to morphisms.
morphisms to morphisms. And this is where it gets kind of intriguing. Okay. So we've been dealing with kind of mapping for each pair of an object in this category and an object in this category. Except here we have arrow of C, right? We're really now dealing with arrow C, but I've shown it for this, just reminding you of how these profunctor collages work. For any two pair of arrows, there's some set of morphisms, of heteromorphisms, these bridges between them. And these are going to allow us, when we reason about it, we lift the profunctor. You may remember that when we have a profunctor, we can lift it on a morphism into this. So if we consider the set of maps from B to C, set of bridges from C to C, set of heteromorphisms, and we give it a morphism from A to B, then we can lift that morphism to give us the set of paths from A to C. So if we have the paths from B to C here, these heteromorphisms, and we have a morphism from A to B, we can lift that set of paths to be set of paths from A to C. You may or may not remember that. If you don't, I'll just remind you, profunctor, this one, and it's exactly what we talked about sort of in a Haskell'ian context when we were talking about this. Remember that? So the feature of a profunctor is it not only maps objects to objects, here a pair of these objects into a set of heteromorphisms from A to B, but it maps morphisms F going from A prime to A, such that if you have the set of maps from A to B, you can get a set of maps from A prime to B, for example. But you can also do it downstream in a covariant way. If you have a map from B to B prime, if you have both of these maps, one contravariant, one covariant, you could turn a set of ways going from A to B into a set of ways from going from A prime to B prime, going something upstream to something downstream of upstream of A to something downstream of B. And so it is here. If we have a set of maps from B to C, and then we have some particular length from A to B here, and some particular length from C to D, that for every one of those lengths from B to C, we will get a link from A to D, namely the one, follow that particular link from B to C down to D. That's the rule of profunctors. And we're going to follow that here. When we lift, we're going to lift morphisms. So we've been doing this on objects. Now we got to think about how the profunctor acts, the action of the profunctors, how they like to talk about it in Cat Colab here on morphisms. Well, morphisms, so to reason about that, we have to reason about morphisms. With precomposition, we're dealing with morphism. So we're dealing with a profunctor from C to arrow of C category, from category C to category arrow of C. So precomposition will be in C. If we have a bridge from C to arrow of C, a heteromorphism from C to arrow of C, a particular length, and we could precompose it with a flow in C, that's over in C land, or we can postcompose it with a flow. See, we could precompose it with a morphism in C, which happens to be a flow. Or we could postcompose it with a morphism in arrow of C, which is one of these commuting squares. Right? So we're just saying we can, if we have one of these bridges, I'll just do it with this. If we have one of these bridges, we can precompose it with a morphism over here in the left category, or we can postcompose it with a morphism here in the right category. Here they happen to be the same shown, but okay. So we got a reason about this. What does this profunctor do? Well, let's think about it. Okay, I'm just drawing on Evan's beautiful exposition of that. Okay, if we have a profunctor from C to arrow of C, so we have a map, and here it's contravariant. So we're starting in B. We have a morphism in C from A to B. Well, a morphism in C is a flow from A to B. We're considering it, okay, it's like we're at this end, but we're going to be able to push it upstream, just like here, we're here, push it upstream. We need this to be coming down into us, and that will allow us to reason about using this as a starting point. Okay, so that's what we have here. And we have a link. This is our bridge between the two categories. This is arrow of C here. This is a morphism in arrow of C. This is a morphism in C. We have this link here. Okay, so this is specifying that F depends on, as a flow, its value depends on the stock B. Okay. Okay, so what do we get out? Well, we're going to have three types of profunctor actions here. One is going to involve precomposition, and this one is kind of interesting. What this is saying is, look, if F depends on B, F depends, it kind of depends. If F is influenced by B, it's also influenced by A. I'll put it that way. This doesn't say the ODEs, like the equations behind this, we map this to semantics, have to have F depending directly on A. No. That's a separate matter. We can reason about this compositionally here. This is one of the insights Evan gave. This is one of the things he said last week, without committing to this, the formula of F depends on A. No. It just says, look, if F depends on, this is the way I think about it. If F is influenced by B, then it's influenced by A as well, upstream of B. Because B, the idea is it has stuff that flowed out of A. So it's influenced by this. So this is kind of pre-composition. This is kind of our equivalent of saying, well, if we have this particular link in green from B to C, then if we have a path from B to C with this particular link, then we have a path from A to C. Okay, good. So that's pre-composition action here. And this is in the CATCO lab. This is supported in CATCO lab. And a link from B to F, here we go, can be pulled back along a morphism. Pull it back to give a link G, and then L, A to F. I prefer if this were written with a semicolon, but G and then L, right? We do G1 and then L. Okay, here's another post-comp. Now we have post-composition. So we're dealing with like post-composing here. If we have a link from if we have a link from B to C, and we're dealing with how do we get to D? Well, we can write a morphism down here in this arrow category. And what do morphisms in that arrow category look like? They look like this. So here, if we have a link from A to F, we can push it forward along. So we have a link to A to F. We can push forward along a morphism from F to this other map to give a link from A to the composition of these two. So if we have F up here, and I should have said we have a G flow from Y to Z. So F goes from X to Y, and we have a flow G that goes from Y to Z. Then we can get a composite morphism. This is just composition, how composition in this category C works. If you have stock A to B with a flow, and then B to C with a flow, you can compose them in C to get a flow from A to C. Again, it doesn't say the ODEs have that flow in them. What it's saying is that compositionally, that there's a second order flow from A to C. And in fact, in system dynamics, it's called a second order. It's called it will be called a second order flow. Again, it doesn't mean that is operating in the ODEs. It's a result of the compositionality. So these two could compose to get a map from A to Z. And in that map, from X to Z, and that map is F followed by G, F composed with G. And it says, hey, if we have a link from A to F, if A influences F, then A influences F going to G, the composite flow. If it influences F, it's got to influence F post-composed with G, so that composite flow, because F is part of it. This is what that looks like. This is post-composition. It's kind of, you have one of these, that's the link, and we're pushing down here in these maps. Okay, that's post-composition 1. Post-composition 2 is kind of post-composition 2 is kind of interesting. Okay, look. If we have a situation where we have F, a flow F from X to Y, and a flow G from Y to Z, then if we have a link from A to the composite from X to Z, notice this is Z here, this is ID, the ID flow from it to itself. So we have a link from A to F composed with G. We can kind of quotient that out at some level to say A. So if we say A influences F composed with G, that composed flow where G is downstream, then A influences G because it influences it kind of through F, right? Through F. It's kind of we recognize that it influences G via F. Here's L quotient F. This, remember, for this to be a morphism in this category, arrow C, it has to compose. And so we're kind of restricted to, in the number of cells that where this composes. Now, I may well be wrong here. I've got to check this with Evan, but my own thinking was that there's also this case where, and I don't know this is the case. I'm still learning this just like you, but if we have a situation where we have a flow here, an arrow C from X to W, call it F, flow F. And we have another one in arrow of C from W to Z, from W to Z, called G. Mm, mm. And such that we have a flow, X to W, F, W to Z, called G. We can get a composing, this square can compose like this, right? With G on this side, F on this side. And if we have a length from A to F, again, that's kind of upstream of G, right? X to W is upstream of G. Then it follows we have an influence from A to G. This is kind of this, it's almost the same thing as this in a way. It's just like we could write it with this square and get this link, where essentially this is a link from A to G that's induced by this. And that's something similar to what we had for post-composition 2. But with post-composition 2, we had A pointing directly at a composite flow from F to G. Here it's, we're pointing at an F, and we're saying, well, if it points to F, well, and G follows F in the structure, then A influences G too. Anyway, these are some thought-provoking implications of the idea of using a profunctor in this sort. And we're thinking over, does this make sense? Cheyenne had a brilliant point with this, that, this idea of kind of pulling back, saying, well, if B influences F, A influences F. And one of her comments was, again, brilliant, how if G1 is a flow whose value doesn't depend on A? Yeah, it flows out of A, but it doesn't depend on the value of A. And that could be. You can imagine something where it draws down A, but it doesn't depend on its value. She said, well, is it really right to say then F depends on A upstream of this? It flows out of it. It drains it, but it doesn't depend on it directly. So these are some things to be thought about. But, there's a question. Is this going to be an adequate model? Does this give rise to a model that is adequate of stock and flow categories, or rather primitive system structure diagrams? And this remains to be seen. But it's certainly an interesting attempt, and it makes you think about compositionality in system structure diagrams or primitive system structure diagrams. Just like what we had here made us think some about capturing, the inherent compositionality associated with causal loop diagrams. And it may be that we refine it and, have another way of representing it. But it's certainly a thought-provoking initial attempt. In practice, it's there, it's working, and it forces us to think, are these useful concepts for stock flow diagrams? To think about explicitly about what influences what. And could these inform us about what influences what, using a language or notions that were previously just latent or tacit? We didn't have any formalization of them. We didn't verbalize them often. So it's forcing me to think. But that is how, right now, as we speak, if you go and you build a causal loop a system structure diagram, stock flow diagram in CatColab, that is the theory that is enacted. Those are the types of models that are enacted. Those are the type of ways in which we capture links and where we can reason about influences. That is all we have time for today.